Good morning student. Welcome to TYBSc Organic Chemistry lecture series. Myself Dr. Kailas Labhade, Associate Professor, Department of Chemistry, S.V.K.T College, Devlali Camp, Nasik. Today we are going to see elimination reaction. This chapter is included in your TYBSc Chemistry syllabus of first term. Now session agenda of this chapter. We are going to see introduction of elimination reaction. In this chapter, we are going to see types of elimination reaction, that is 1,1 elimination, 1,2 elimination, general mechanism of E1 elimination, E2 elimination, E1 CB elimination, mechanism of E2 reaction with evidences, and finally, we are going to see Hoffmann and Saytzeff elimination. Learning objective. At the end of this session, students should able to understand what is elimination reaction, what is 1,1 elimination, what is 1,2 elimination. They should able to write mechanism of E1, E2 and E1 CB reaction. They should understand what is Saytzeff elimination, what is Hoffmann elimination, and they are able to predict the product on the basis of Saytzeff and Hoffmann elimination rules. Before starting our elimination chapter, we should know the different type of organic reactions. There are 4 types of organic reaction: addition reaction, substitution reaction, elimination reaction, and rearrangement reaction. In addition reaction, 2 reactants added together to form a single product. For example, HCl, when added to ethylene, there is formation of ethyl chloride. In substitution reaction, an atom or group from substrate molecule is substituted by another atom or group. In this case, chlorine atom is replaced by hydroxyl group. Third type of reaction is elimination reaction. In elimination reaction, 2 atoms are removed from substrate molecule to produce a product with higher degree of unsaturated. And another type of reaction is rearrangement reaction. In rearrangement reaction, there is change in carbon skeleton of the starting compound. This is the example of Hoffmann rearrangement. Starting compound is amide and product is amine. There is change in carbon skeleton of the molecule. Now, elimination reaction is the reaction in which 2 atoms or group of atoms are removed from the reactant to form a product with higher degree of unsaturation. In this case, 2-bromopropane is the starting compound. When it is treated with base like sodium ethoxide, base abstract that beta proton, and after that loss of bromine produce a product with higher degree of unsaturation. In this case, propene is the product. Now type of elimination reaction, 1,1 elimination. In 1,1 elimination, both atoms or group, they are departed from the starting compound belong to same carbon atom. This is the example of 1,1 elimination. In this case, hydrogen and chlorine atom, which are associated with same carbon atom, they are eliminated and there is formation of dichlorocarbene as the product. These are some features of elimination reaction, 1,1 elimination. It is also called as alpha elimination. This type of elimination reactions are less common. Mechanism of these reactions are similar to E1 CB mechanism. First step is generation of carbanion and second step involve loss of leaving group. Another type of elimination reaction is 1,2 elimination. In 1,2 elimination, loss of 2 atoms or group that is take place from adjacent carbon atom. It is also called as beta elimination. 1,2 elimination, these are some example of 1,2 elimination. Dehydrohalogenation, removal of hydrogen as well as halogen, that is called dehydrohalogenation reaction. And this is the example. This is the alkyl halide. When it is treated with alcoholic base abstract that proton, and there is elimination of HBr from starting compound, and finally alkene is the product. In this case 2-butene is the product which is obtained during dehydrohalogenation reaction. Second type of 1,2 elimination reactions are dehydration reaction. In dehydration, there is loss of water molecule. Dehydrating agent like concentrated sulfuric acid, Al2O3 or phosphoric acid can be used for this reaction, and overall there is elimination of H2O from starting compound. This is another example of 1,2 elimination, that is dehalogenation, means removal of 2 halogen from starting compound. This is the vicinal halide. 2 bromine atoms are present on adjacent carbon atom. When this compound is heated with zinc or magnesium, there is loss of Br2 from the starting compound. This is called dehydrohalogenation reaction. And fourth type of 1,2 elimination is pyrolytic elimination. In pyrolytic elimination, ester, when they are heated at high temperature, there is formation of alkene. These are 4 types of 1,2 elimination reaction, and these are the examples. Now substitution versus elimination. What is the difference between substitution and elimination? We have already studied during earlier classes. In substitution reaction, the atom is substituted, atom or group is substituted from the substrate molecule, and in elimination reaction there is loss of small molecule. Tertiary butyl bromine, when treated with base like NaOH, there is formation of tertiary butanol, is the example of substitution reaction. And when this tertiary butyl bromide react with base in presence of alcohol, there is formation of alkene as a product. This is elimination reaction. Substitution versus elimination. For substitution and elimination, we require base as a catalyst, and proportion of substitution and elimination depend upon several factors. Strength of base is the first factor. When strength of base increases, percentage of elimination increases. In second example, strong base like sodium ethoxide is used, and in that case elimination is predominant. Another factor that affect the substitution and elimination reaction is the nature of base, that is bulkiness of base or nucleophile. In first case, this reaction is carried out in presence of HBr. Br is smaller in size as compared to ethoxide. In second case, same reaction is carried out in presence of H2SO4. Here, conjugate base of H2SO4 is HSO4 minus, and in first case, conjugate base of HBr is Br minus. Size of Br minus is much smaller than size of HSO4 minus. That's why in second case, elimination is predominant. Hence, as the size of attacking base or nucleophile increases, percentage of elimination reaction also increases. And third factor that affect the substitution and elimination, that is the temperature. When temperature is high, it favors the elimination reaction. Now, mechanism of beta elimination or 1,2 elimination. This is the substrate molecule, that is alkyl halide. So alkyl halide on reaction with base, there is formation of product. In this case, alkene is the product which is obtained. In beta elimination or 1,2 elimination, there is breaking of C alpha X bond is take place. There is breaking of C beta H bond is taking place, and there is formation of C alpha C beta pi bond is taking place. Types of 1,2 elimination reaction or beta elimination reaction. There are 3 major types of 1,2 elimination reaction, that is E2 elimination. It is also called bimolecular elimination. E1 elimination, it is also called unimolecular elimination. And third one, E1CB, that is elimination unimolecular via conjugate base. We are going to see the general mechanism of all these three elimination reaction. First of all, E2 elimination. This is the example of E2 elimination, N-propyl bromide on reaction with sodium ethoxide produce propene as a product. This reaction proceeds through single transition state. These are the features of E2 elimination. It is bimolecular reaction, that is the rate of reaction depend upon substrate as well as base. Concentration of substrate as well as concentration of base affect the rate of the reaction. All bond making and bond formation taking place simultaneously. That's why it is concerted mechanism. This reaction proceeds through single transition state and it is one step mechanism. Now E1 elimination. This is the example of E1 elimination. E1 elimination is unimolecular elimination. Rate of reaction depend upon the concentration of substrate only. Concentration of base does not affect the rate of the reaction. In first step of E1 elimination, there is formation of carbocation. Leaving group leave the molecule with electron pair and carbocation is formed. In second step, base abstract beta hydrogen and there is formation of alkene as the product. Role of base is in first step. That's why concentration of base does not affect the rate of E1 elimination. In E1 elimination, carbocation is formed as an intermediate and we know that carbocation can rearrange itself from primary to secondary or secondary to tertiary because stability of carbocation is tertiary greater than secondary greater than primary. Hence, rearrangement is possible in E1 elimination. Third type of reaction is E1CB elimination. In E1CB elimination, first step is formation of carbanion. Base abstract that beta hydrogen and there is generation of carbanion. And in second step, the negative charge or the electron pair which is present on beta hydrogen is utilized for formation of carbon-carbon double bond between alpha and beta carbon atom. Abstraction of proton by base is taking place in first step. That's why its rate is depend only on the concentration of substrate molecule. It does not depend on the concentration of base. Intermediate carbanion form in first step. It is two-step reaction. The mechanism is less common as compared to E1 and E2 elimination. Now we are going to see mechanism of E2 elimination in detail. This is first example of E2 elimination. Alkyl halide is the starting compound and base can be used, that is sodium methoxide or sodium ethoxide. This type of base is used for this reaction and alkene is the product which is obtained. This reaction proceeds with single transition state. We have already discussed that. Base abstract that proton and there is a Y group which is leaving group in this substrate molecule that leave the molecule. All that taking place simultaneously and that's why it is one step mechanism or single step reaction. Kinetic of this reaction. Rate of reaction is proportional to the concentration of alkyl halide as well as concentration of base. Rate is equal to K into concentration of alkyl halide into concentration of base. This E2 elimination involves the transition state. In transition state, two bonds are formed, two bonds are broken, that is CH and CY, and two new bonds are formed, that is carbon-carbon double bond, and there is another bond which is formed between base and hydrogen atom. Evidences of E2 mechanism. First evidence is kinetic isotopic effect. We know that kinetic isotopic effect is used to study the reaction mechanism, which step in the reaction mechanism is slow step or which step is fast step, that can be decided or that can be find out on the basis of kinetic isotopic effect. In kinetic isotopic effect, normal substrate molecule and deuterated substrate molecule, they undergo reaction with same reaction condition, and finally rate of both reaction is measured. If rate of both reaction is equal, then we can say that breaking of CH or CD bond is taking place in fast step. In E2 elimination, Kh upon Kd is equal to 7. This means that first reaction or first substrate reacts 7 times faster than second substrate. Hence, we can say that breaking of CH or breaking of CD bond is taking place in slow step, because we know that energy required to break the CH bond is much less as compared to energy required to break CD bond. Second evidence, nature of leaving group. In this case, RCH2CH2X is the alkyl halide and the product is RCH double bond CH2. Alkene is the product. Here we change the X. X is fluorine, chlorine, bromine and iodine. In first example, relative rate is considered as a 1. With respect to this relative rate, second compound, that is 2-phenyl chloroethane, it react with the rate 70. Third compound react with the rate 4.2 into 10 raised to 3, and fourth compound, where iodine is the leaving group, rate of the reaction is 3.7 into 10 raised to 4. We know that leaving group ability in this alkyl halide is iodine greater than bromine, greater than chlorine, greater than fluorine. Means iodine is the good leaving group and fluorine is bad leaving group. That's why as the leaving group ability increases, rate of E2 elimination also increases. Third evidence, absence of hydrogen exchange. In order to prove that the reaction follows E2 mechanism and not E1CB, hydrogen exchange experiment is carried out. For example, 2-phenyl ethyl bromide is allowed to react with sodium ethoxide in presence of deuterated ethanol. Reaction is allowed to proceed until half and then arrested. This is the reaction in which OET group withdraw that proton and there is formation of carbanion. If reaction follows E1CB mechanism, then unreacted substrate should contain deuterium. In actual experiment, unreacted substrate did not contain deuterium. This means that there is no hydrogen exchange. Hence, we can distinguish E2 elimination from E1CB elimination by using this hydrogen exchange experiment. Now, orientation and reactivity in E2. Saytzeff rule. In an elimination reaction, more substituted alkene is obtained as a major product. When alkyl halide containing only one type of beta hydrogen atom, in that case only one product is possible. But when alkyl halide containing two types of beta hydrogen or more than two types of beta hydrogen, in that case more number of products are formed, and the major product in that case is given by Saytzeff rule, and this rule states that more substituted product which is obtained in an elimination reaction is major product. Now let's consider this example. In this case there is only one type of beta hydrogen atom is there. That's why only one product is possible in this reaction. But in second example there are two types of beta hydrogen atom. That's why two types of products are possible. One product is major product and another product is minor product. In this case, first product is major product because it is more substituted. It is di-substituted product. and second product is mono-substituted product. That's why it is less substituted. According to Saytzeff rule, more substituted product is major product. This is another example of Saytzeff rule. In this case also there are two beta hydrogen atoms are present. When this substrate molecule undergo reaction with alcoholic KOH, there is formation of two product, 2 butene and 1 butene. Percentage of 2 butene is 80%, that is it is major product, and percentage of 1 butene is 20%, it is minor product. 2 butene is more substituted, that's why it appear as a major product. This is next example. In this case also there are two types of beta hydrogen atom. 2 pentene and 1 pentene are the product. Percentage of 2 pentene is 70%. Percentage of 1 pentene is 30%. 1 pentene is mono-substituted product. 2 pentene is di-substituted product. That's why more substituted product is obtained as a major product. And this is third or another example. In this case also 2-methyl-2-butene obtained as a major product. 72% yield is obtained because it is tri-substituted alkene, and second product is di-substituted alkene. It is obtained in 28%. Now justification of Saytzeff rule. Why this is going to happen? Why more substituted product is major product and why less substituted product is minor product? That we are going to see. That is justification of Saytzeff rule. Now stability of alkene. Stability of alkene depend upon the heat of hydrogenation. When heat of hydrogenation is less, then that alkene is more stable. Here there are some example. First is 1-butene. It is mono-substituted alkene and heat of hydrogenation is 30.3 kilocalorie per mole. Heat of hydrogenation is the energy or heat evolved when there is addition of hydrogen across carbon-carbon double bond. In second case, it is 2-butene, it is di-substituted and its heat of hydrogenation 28.6 kilocalorie for cis and 27.6 kilocalorie for trans. If we compare the heat of hydrogenation of 1-butene and 2-butene, we can find that heat of hydrogenation of 2-butene is less as compared to 1-butene. This means that 2-butene is more stable as compared to 1-butene. If you consider cis and trans stability, then trans isomer is more stable as compared to cis isomer. These are another two examples of the stability which is depend upon the heat of hydrogenation. As number of substituent increases, stability of alkene also increases. Stability of alkene depend on heat of hydrogenation. We have already discussed heat of hydrogenation is the heat liberated during addition of hydrogen across carbon-carbon double bond. Lower the heat of hydrogenation, more is the stability of alkene. Now let's see. Here there are three examples. Mono-substituted alkene is shown. In second example, di-substituted alkene is shown. And in third case, tri-substituted alkene is shown. Heat of hydrogenation is decreasing from example number 1 to example number 3. This indicates that tri-substituted alkene is more stable as compared to mono-substituted alkene. And this is the general order of stability of alkene. Tetra-substituted alkenes are more stable as compared to tri-substituted. Tri-substituted are more stable as compared to di-substituted. And these di-substituted are more stable as compared to mono-substituted. This is second justification for Saytzeff rule, lower energy of activation. In this case, 2-bromopropane is the starting compound. Base is used for this elimination reaction and two products are obtained, 1-butene and 2-butene. If you see this diagram carefully, we can find that energy which is required for formation of 2-butene is less. That energy of activation for formation of 2-butene is less as compared to energy of activation for formation of 1-butene. This indicates that 2-butene is formed with faster rate, or it requires less energy to achieve the transition state. This is the third justification for Saytzeff rule, stability due to resonance effect when double bond produced is in conjugation with benzene ring or is in conjugation with another double bond, then stability in that alkene increases. In this case, two products are obtained. In first product, that double bond which is generated is in conjugation with the double bonds which are present inside that benzene ring. In second example, that double bond which is generated is not in conjugation with the double bond which are present inside that benzene ring. Hence, first product is obtained in 95% and second product is obtained in 5%. This means that if conjugation is there, then stability of that alkene is more. Now in this case, there is formation of two products, 3-methyl-1-phenyl-1-butene. In this example, that double bond which is generated is conjugated with that benzene ring, and in another product, 3-methyl-1-phenyl-2-butene, that double bond is not in conjugation with double bond which are present inside the ring. That's why second product is minor product and first product is major product. In conjugated alkene, extra stabilization by resonance is possible. Now there is another type of elimination that is called as Hoffmann elimination. In Hoffmann elimination, this is exactly opposite of Saytzeff elimination. According to Hoffmann rule, in an elimination reaction, less substituted alkene is obtained as a major product. When substrate contain more than one type of beta hydrogen atom, then more than one products are possible. Let's see this example. In this example, leaving group is NCH3 thrice, means size of that leaving group is large. When this type of substrate molecule react with alcoholic base, there is elimination reaction, and in such cases major product is given by Hoffmann rule. In this case, 1-pentene is obtained as a major product and 2-pentene is obtained as a minor product. Means first product is less substituted, but it is obtained as a major product. Second product is more substituted, it is obtained as a minor product. But these products are according to Hoffmann rule or Hoffmann elimination rule. Factors that affecting Saytzeff and Hoffmann orientation, the effect of leaving group. Let's see this. X is leaving group, and there are different leaving group shown in this table. Br is the first leaving group. As we know that size of leaving group, that is Br, is small. In that case, percentage of Saytzeff product is more, 80% Saytzeff product and 20% Hoffmann product is there. In second case, OTS, tosylate group is there, size of leaving group increases. Percentage of Saytzeff product decreases, it decreases from 80 to 60%. Hoffmann increase from 20 to 40%. Hence, as the size of leaving group increases, percentage of Hoffmann product increases. In third case, leaving group is SCH3 twice. In this case, 75% of Hoffmann product is obtained. And in fourth case, size of leaving group is much large as compared to bromine. That's why percentage of Hoffmann product is 95% and percentage of Saytzeff product is 5%. As the size of leaving group increases, percentage of Hoffmann product also increases. Then effect of base. effect of attacking base also determine the percentage of Saytzeff and Hoffmann product. Size of attacking base is very important. In this case, we have shown some bases C2H5O, that is ethoxy. Size of base is very important. From first, second, third, size of base increases. In that case, percentage of Saytzeff product decreases and percentage of Hoffmann product increases. As the size of attacking base increases, the transition state for Saytzeff elimination become more crowded than Hoffmann elimination. Thus, percentage of Hoffmann product increases. And in this diagram, it is shown that how transition state is affected when size of base is large. In second example, attacking base is present at the terminal of that carbon chain. That's why its interaction with other group is minimum, and that's why we can say that less crowded transition state is there for Hoffmann elimination, and that's why Hoffmann product is increases. Summary of today's lecture. In this lecture, we have discussed what is elimination reaction, what is 1,1 elimination or alpha elimination, what is 1,2 elimination or beta elimination. We have seen general mechanism of E1 elimination, E2 elimination and E1CB elimination. In E1 elimination, carbocation is intermediate and it is two-step process. E2 elimination is one-step process and all bond breaking and bond formation taking place simultaneously. E1CB elimination is also two-step mechanism. In first step, there is formation of carbanion. Then we have discussed Hoffmann rule and Saytzeff rule, and we have discussed different factors that affect the Saytzeff and Hoffmann orientation. In next lecture, we are going to see mechanism of E1 elimination in detail, stereochemistry of E1 and E2 elimination, orientation and reactivity in E1 elimination. In that, we are going to see how rearrangement are going to take place in E1 elimination, because in E1 elimination carbocation is intermediate and we know that carbocation can rearrange to more stable carbocation. Thank you.